Hello, my name is Trevor Brenningson, and I am a senior here at USF.
Hi, my name is Ibrahim Mansour. I'm a senior electrical engineering at USF.
My name is Salman Farhan, and I'm a senior electrical engineering student here at USF.
My name is Quentin Rogers. I'm a senior at USF in electrical engineering.
So we're Smart Farm IoT. Our advisor is Dr. Wilfredo Moreno. But why Smart Farm IoT? How did this project come to be? Well, Software Logistics, a company that provides custom solutions for companies through the usage of IoT technologies, approached USF to sponsor a Capstone project by making the resources available. And that's Kevin, our sponsor. It also happened that the Hillsborough County has a project to implement smart farming into small farms to help them grow their businesses and promote local farms through their extension small farm with partnership with UF. According to USDA, about 90% of those farms in Florida are small farms, and Hillsborough County accounts for about 7% of those. And that's Francisco, which is our subject matter expert. As Kevin said, building a comprehensive IoT is expensive and time consuming, making it cost prohibitive for small farms. And that is where NovaIoT comes into play, a software logistic product which makes simple the deployment of monitoring of IoT systems. Instead of the traditional coding way, it is mostly the configuration of parameters. Data can also be stored over time and used for analysis later on. So we have a sponsor, a subject matter expert, and the targeted market. Now we're missing a client, a small farmer. Alvaro, owner of Florida CG, allowed us to use his nursery for the first portion of our project. Now let's go to our design. The system design will be comprised of two main applications: a plant-based greenhouse farm and a cattle-based cattle farm. And both will be sending data to NavIoT. For the growing chamber, the end user wanted to monitor the condition of the chamber. As it was old, he did not know the ambient temperature and humidity as well as the soil moisture of the plants present. That information will be made available for him and also stored on NavIoT. For the pH monitor, the end user expressed a need to know the pH level of water coming from the well which he uses to water his plants. As it changes throughout the year, having that information will allow him to make the appropriate mixtures of solution he needs to meet his desired pH level. The pH level and temperature of the water will be made available for him on a display, and the pH level will be sent on NavIoT. For cattle collar, the end user expressed a need to determine when the cow is in heat, which will help increase the breeding chances for farmers. As discussed with the subject matter expert, monitoring the temperature would be the practical way for this application. Also, the location of the cow will be tracked. For pest control, the need was to manage cattle flies as they can cause significant weight loss, about 20 pounds in some extreme cases, as well as stress and disease, affecting the farmer's revenue. Thus, a fly detection model was made, and whenever motion is sensed, a picture is taken and sent on NavIoT servers for analysis. Now let's start with the pH monitor. So we have the sensor hooked to an Atmega, which will gather the pH and the temperature of the water, send that through Bluetooth to the hub. And the hub is comprised with an ESP32 hooked up with an HC05, which actually gets that data and sends it through serial connection to the Raspberry Pi, which then displays it on a little LCD tablet and on a web page as well. So Alvaro has access to it. And that information is also sent on NavIoT, as mentioned previously. As you can see here, this is the PCB as well as a power bank and the 5-buck converter. As you can see, we're just making an install. And that's what it looks like. Here it's data being received and sent through serial connection on the Raspberry Pi and being displayed on the LCD display. Now the cattle collar. It is a ESP32 connected with the IR sensor, a battery pack, a voltage booster, a charger, the modem, and the GPS. As you can see, it's the box. Here's the data coming in on Nav IoT with the temperature and the GPS location. And here's just the code. We're going to skip through it. As you can see, just defining our the serial connections, connecting to the modem, defining the device name as CCDev, so that way when the data arrives on Nav IoT, we know which the cattle was sent from. Gather that information, send it on Nav IoT, obviously make the connection through the modem, establishing internet, send that information, and also displaying on serial monitor the location and the temperature. So an IP camera is used, and whenever motion is sensed, a picture is taken, sent to Nav IoT through FTP, and then when first it goes to a first model to detecting cattle. If cattle is detected, then it goes to a second model, which is fly detection, and then fly is detected, then it sends a message, a text message, to act as a command of sparing pesticide. If not, it goes back to the loop. And here, as you can see, I'm just showing how I trained one of my models, the cattle model. First, I'm importing data. I'm importing the FASTA libraries, which then I import my data set, which is mounted on my Google Drive. Once I get it, then I take 20% of those pictures to be used for validation purposes. 80% will be used for the training. I'm resizing the images to 128 pixels for faster upload. And then I'm augmenting my data by changing the size to 224 pixels, which is standard for image processing. And then I'm cropping the pictures by portion so that it would have more data, and also the model would be able to determine, even if it's only on the picture there's only half a cow, like if it's a leg and back or back and head, the cow. And here, as you can see, I trained the model for only 15 epoch and I got 95.6%. I'm using a ResNet 50, a convolutional neural network. And as you can see, the validation and training loss are both dropping, but the training loss dropped faster than the validation loss, which proves that the model is actually learning and being more confident about its choices. To demonstrate that, I'm also gonna show I'm just gonna train the model for just 4 epoch to show that even though after 4 epochs it had 91.8%, it doesn't mean that the model is confident of its choices, as the training loss and the validation loss are equal. That also shows that the model tend to be overfitting. We can also see on the confusion matrix that on 13 pictures, the model predicted them as being single cows in the picture, but actually it was there were multiple. And afterwards, just save my model as a ONX file, export it so that it can be run on Nav IoT servers. And for the PyTorch, I exported as a PyTorch file, PKL, which can be used locally on the machine. I'm just going to show how to set up configure parameters on Nav IoT. First, we go to Studio and then go to Make. I'm going to go device message type. There are many others to be set, a few more, but for this purpose, I'm just going to show you 2. This one is the message type, and then we're going to growing chamber. put the name and key, and then set up message ID and then message direction for us as incoming messages. For the content type is going to be JSON, as we can do HTTP post. And then you put as many fields as you want: temperature, humidity, and soil moisture for growing chamber. Here I'm just showing you for the temperature. The message we're going to search for in the message body, and then the field type would be float, storage field would be decimal, and then we'll say is required, so that when the JSON path is not found, it would say there's an error parsing that message. So the same thing we'll do for humidity and soil moisture, the same principle. This time I'm going to show you the device configuration, as there are other more parameters, but for time's sake. So for the GC device, again, put a name, a key, and you put the routes that you want. For us is temperature, humidity, and soil moisture. So since we did temperature, I'm just going to stick with temperature. For message definition, the message type we just created, we put it over there as message definition. And then Sentinel is basically, we can put an identification if we wanted to, but we'll keep it as anonymous. And input, as the message comes in, we could map it to a handler. In our case, it was temperature, so we select GC temperature handler. And we can also make the input go into a data stream so it can be stored. And we decided to create a data stream called GC temp. And as you can see, we can map the input with the workflow. So as the message comes in, the message field is temperature. It will map it to the workflow, which is GC temperature. So the parsing of the message is actually being done right there using it. Now we can see the graphs as the data comes in. Soil moisture is around 86%. The humidity increased by like 81%. And the temperature around 73. And these are the data for the past 2 hours. And as you can see on the right, the data as it comes in, exactly temperature, humidity, and soil moisture. This one is for the pH. As you can see for now, on the gauge, it's about 7.3, and it's high because the end user Alvaro wants his pH to be between 6.2 and 6.5. So that means he's got to make some adjustments. But here, and that's it. Thank you. So as I mentioned earlier, when we do the data stream, we could store the data. Now here using Postgres, you can actually access that data as it's been stored on the data stream. As you can see here on the left, we did a list of repositories, and the one we're actually interested in was the sensor reading repository. Once we get there, we can obtain that data and do some quick analysis using SQL language. For this one, we're doing a basic one. We're doing an hour timestamp interval, and we're doing an average on the temperature from sensor readings, and on a 2-day period from March 10th from 9 a.m. to March 12th to 10 p.m. As you can see here, at the beginning in the morning, the average was 88, and then 87, 89 as the day goes by. I mean, at the reaches of the afternoon and the nighttime, temperature increases up to 94, 93. That shows like it was a pretty hot night. And as the morning comes, actually temperature is decreasing. That's about it. As you can see on Postgres, we can do some quick analysis. Thank you.